Welcome. Please subscribe the channel if you are new to the channel. Let's start. What is partial ordering? A relation R on set S is called a partial ordering or partial order if it is reflexive, antisymmetric and transitive. A set S together with partial ordering R is called a partially ordered set and is denoted by S, R, this ordered pair S, R. The point I hope you must have noticed that in case of equivalence relation, we wanted the relation to be reflexive, symmetric and transitive, but here we want it to be antisymmetric. To understand this, let us take few examples. The first example is that suppose on the set of integer I define the relation R, and how this relation R I have to write like this because this is the representation of real number. So I am defining the relation R on the set of integer. How I am defining the relation R? That an element A is related to element B, means A comma B belongs to R if A is greater than or equal to B. Check whether it is satisfying the requirement for the relation to be partial ordering or not. It is reflexive, very obvious that every element A is greater than or equal to A. This is true for all elements A that belongs to the set of integer. Every element A is greater than or equal to A means A comma A belongs to R. So that is why it is a reflexive relation. Second, antisymmetric or antisymmetric. Now you are smart enough to understand that if I take any two integer, like if I take for example 3 and 7, so 3 comma 7 is not in R. Why it is not in R? Because 3 is not greater than or equal to 7, but 7 comma 3 is in R. Why? Because 7 is greater than or equal to 3, right? So if A comma B is in R, then B comma A is not in R. Now this is important to note here that some of you might have thought that what is the definition of antisymmetric relation? That if A comma B belongs to R, then B comma A should not belong to R. But they may belong in case when both A and B are equal. So in case suppose you say that A comma B belongs to R and B comma A also belongs to R, then in that case A and B will be equal. So this relation is certainly antisymmetric. I hope when I am writing this you are clear about this idea that if A is greater than or equal to B and B is also greater than or equal to A, that will be possible only when both A and B are equal. And finally, if I talk about the transitive property, that is very obvious. Why it is very obvious? That if A is greater than or equal to B and if B is greater than or equal to C, means if A is related to B and B is related to C, then certainly A will be greater than or equal to C. So this is also a transitive relation. So this relation, the relation that I have defined on the set of integer that is greater than or equal, is a partial ordering because it is reflexive, it is antisymmetric and it is transitive. I hope I am making sense to you. So let us take the next example, that is the divisibility relation. And I hope you understand this notation stands for division. So suppose somewhere it is written A and B like this, then it means that A divides B. You should not confuse it with A by B, right? Because when we write A by B, we write something like A by B, slightly slanted line, but here we are writing a vertical line. So on the set of integers Z, I am defining the relation, that is the divisibility relation, that two elements A comma B are belonging to the relation, or I say that A is related to B if A divides B. Yes, gentlemen and ladies as well. So if A divides B, then A comma B is related to, A comma B belongs to R. So let us check whether it is partial ordering or not. So is it reflexive? I think you will all agree that every element A divides itself. So A comma A belongs to R for every element A in the set of integer. I hope you agree that 2 divides 2, minus 2 divides minus 2, 1 divides 1, and so on. So divisibility relation is that is satisfying the requirement that it's to be reflexive, right? Now one thing I hope you might be thinking, and some of the students might already have noted, that what if I take 0? So 0 divides 0 is not defined. So when I am talking about this divisibility relation on the set of integers, let me make one small correction here. I am taking the set of integers minus the 0 integer, because if I take 0, in that case this problem will arise. So if it is set of all non-zero integers, then certainly it will be reflexive. I hope you have understood the correction that I have introduced, that here I am taking the set of non-zero integers, set of non-zero integers. Now it is anti-symmetric also, right? I hope you agree that why it is anti-symmetric, because if A divides B, then B does not divide A, right? Because for example 2 divides 4, but 4 can't divide 2. In case if A divides B and B also divides A, that is the situation when A and B will be equal. So I think by the definition of anti-symmetric relation, you understand that the definition requires that if A comma B belongs to the relation R, or if A is related to B, then B should not be related to A, except in those cases when A and B are equal, right? So this is certainly anti-symmetric. And third is that it is transitive. So transitivity, I guess you will be able to understand, because if A divides B, if A and B are related, means A divides B, and suppose I say that B divides C, so there is no confusion to see that A will also divide C. If A divides B, for example, if I say that 3 divides 6 and 6 divides 18, so certainly 3 divides 18. So where is the confusion? So this property is transitive as well. So the divisibility relation on the set of non-zero integers is a partial ordering. I hope you agree to this. Let us take one more example, and this is important example. The inclusion relation is a partial ordering on the set of power set of S. Now to understand this, suppose I take a set A, or suppose set S, because here I am taken S, and it has 3 elements A, B, C. So first of all, I hope you all know that how to write the power set of S. It will have empty set, element A, B, C, A comma B, B comma C, and C comma A, and finally we will also have A comma B comma C. So this set, which contains all the subsets of the set S, is a power set. Now I am saying that suppose we are taking 2 subsets. Let me call this A1 and A2. So I am saying that A1 is related to A2 if A1 is a subset of A2. So this relation is a partial ordering. And why it is a partial ordering? Because it is reflexive. Why it is reflexive? Because since every set is a subset of itself, right? So if I take any two element like A, for example, if I take the element A, then A is a subset of A, this set. So every element is related to itself, so it is reflexive. It is anti-symmetric because from the property of set theory we know that if we have a set A and if A is a subset of B, means if A is related to B, if A is a subset of B means A is related to B, then B is not a subset of A, right? But I hope you also know that if A is a subset of B and B is also a subset of A, this is possible only when A and B are equal. So in general, if A is a subset of B, B will not be a subset of A. But if both are true, means if A is a subset of B and B is also a subset of A, in that case, this this is possible only when both are equal. And the third possibility, so this relation is anti-symmetric also. And what about transitive property? So transitive property is also obvious. You have studied in your set theory class that if A is a subset of B and B is a subset of C, then most certainly A will be a subset of C. So if A is a subset of B means A is related to B. B is a subset of C means B is related to C. Then A will be a subset of C, so it will be transitive, right? So we have seen that this relation is reflexive. This property was anti-symmetric, and and it is transitive as well. So this satisfies all the three requirements for the relation to be a partial ordering. So the next thing that we are going to discuss about comparable and incomparable or non-comparable element. So let us look at the definition first. The element A and B of a partially ordered set are called comparable if either A is less than or equal to B or B is less than or equal to A. When A and B are elements of S such that neither A is less than or equal to B nor B is less than or equal to A, then they are said to be incomparable or non-comparable. Now before I take the example, I need to highlight one thing, that here the notation that I have used for the relation, it should not be confused with the usual ordering, in the sense that less than or equal to. It is basically being used as a symbol for the relation, that if I say that A is less than or equal to B, it simply means that A is related to B, right? Just to highlight the ordering nature of it, I am writing it A is less than or equal to B, right? So to understand this, let us look at this example. Suppose we have taken the partially ordered set Z plus on the set of positive integer, then 3 and 9 are comparable element. Why these two elements are comparable? Because 3 divides 9. Yes or no? If I take 7 and 14, then 7 and 14 are comparable element because 7 divides 14, right? But 5 and 7 are incomparable element because 5 does not divide 7 nor 7 divides 5. So in this case I will write that 5 is less than or equal to 7. Again I repeat it, it should not be seen in the numbering sense that 5 comes before 7. It simply means that 5 is not related to 7 because 5 is not related to 7 because 5 does not divide 7 and 7 also does not divide 5, right? But there may be examples where there is a possibility that every two element or any two elements are well ordered. So suppose if I take a partially ordered set, and if every two elements of S are comparable, then S is called a totally ordered, I highlight it, totally ordered or linearly ordered set, and this relation is called a total order or linear order. A totally ordered set is also called a chain. Now if you take Z less than or equal to is a totally ordered set. Now here see, there are few things that you should be smart enough to understand through the context. When I am taking this example here, Z and less than or equal to this, here this from the previous example you have seen that this is basically the less than or equal to thing. If I say A is less than or equal to B, it means A is related to B, and here I was assuming that this is the less than or equal to in the literal sense, that 2 is less than or equal to 3. So this is a totally ordered set. Why? Let us verify. You take any random 2 element, right? So if you take any 2 random element, then certainly between them you can decide that which one is smaller and which one is greater. Like suppose I take 7 and 23, then I can clearly say that 7 is less than or equal to 23. If I take minus 9 and 0, then I can clearly say that minus 9 is less than or equal to 0. Right. So this is a totally ordered set, and this is called a chain as well, right? But this is not a totally ordered set. The divisibility on the set of positive integer, because you can clearly see that here suppose I say 2 and 6, then 2 and 6 are related because 2 and 2 divide 6. But if I take 3 and 8, then 3 and 8 are not related because 3 does not divide it. So we can't say that whether 3 is neither less than or equal to 8 nor 8 is less than or equal to 3. See, I have deliberately written it so that you understand that by this less than or equal to, I simply mean in this example that 3 is not less than or equal to 8 and 8 is not less than or equal to 3. It simply means that 3 does not divide 8 and 8 does not divide 3, right? So this is not a totally ordered set. I repeat it, some students do get confused with the things about ordering. Just to make more sense of it, let me one very simple example to understand. See, in dictionary, if you usually look at 2 words, you can clearly say that which word come before and which word will come after. Suppose I want to find out that take the 2 2 words like apple and orange, right? So if you take these 2 words, then certainly apple comes before orange, so we can say that apple is less than or equal to orange. It does not mean that less than or equal to is not making any sense here. It simply means that the relation that we are defining, right, that 2 words are related to each other if one word comes before the other word. So here it will be also a partial ordering, because every element is related to itself, and it is not possible for apple to for 2 words, like if I take apple comes before orange, so orange can't come before apple in the dictionary, right? So this is anti-symmetric also. And similarly, if you take any 3 words, then if suppose I say that apple comes before what you call ball, right, and then ball comes before cat, then certainly apple comes before cat. Means we are not going into the nursery class, but the point is that this example, I hope, is making sense to you. Okay, gentlemen and ladies. So the next thing that we are going to talk about is Hess diagram, and this is a very important idea, and sometimes people get confused with it, but it is a very simple idea. So let us understand it. Hess was a mathematician, and we honor people for their contribution. So he has actually developed a process of representing the partially ordered set, and this is a very a smart way of representing the partial ordering. What is it? What basically it is just a neater graphical representation, right? Neater means it is not very clumsy, it is not very bulky, it does not have lot of things in it. So when you see it, it looks visually appealing, it looks very aesthetically beautiful. So that is the point related to the Hess diagram. To make sense of what is a Hess diagram, I will take this example, and let us understand this, ladies and gentlemen, that I am taking a set, and on this set I have defined the divisibility relation. So if you list down all the element, it will be like a very challenging thing. Not a challenging thing, but certainly it will be time consuming, because I have to write 1 1 1 2 1 3 1 4 1 6 1 8 1 12. and then 2 2 2 4 2 6 2 8 2, so like time consuming, or like rather a very boring job. Another way of representing the relation we have seen in earlier videos, I hope you are watching them in the sequential order, is through the graphs, directed graphs. So when we try to draw the directed graph, we have noticed that if the relation is reflexive, then there will be a loop at each of the element or each of the vertex of the graph. So since we already know that it is the diagram which is representing a partially ordered set, and we know that partially ordered set are reflexive, so just removing the loops does not make much difference, because we are already aware that the loops are there, so there is no need to draw it, right? So that will actually make the diagram look neater, more cleaner diagram. So let me draw it. So first is I am taking the element 1 here, right? And when I'll be drawing it, if one element is related to the other element, that element will come over the first element, means we will move in the vertical direction. So I take 2 here. So suppose I take this element 2 and then I join 1 to 2. So I have moved in the vertical direction. So in the vertical direction, it has actually helped in two things. One is that there is now no need to draw the arrow, because we clearly know that we are allowed to move from lower level to upper level, means we are allowed to move only in the vertical direction, right? So that arrow part is also taken care of. Second point is that I have an element 3 over here, so I can join 1 to 3, right? So I can join 1 to 3 in the vertical direction. Now we have the element 4, so let me write the element 4 here, and since 2 divides 4, so I will join 2 and 4. Now some of you might be thinking that, sir, 1 also divides 4. Then see, since we also know that the Hess diagram is being drawn for representing a partially ordered set, and we know that partially ordered set are transitive. So since 1 divides 2 and 2 divides 4, so certainly 1 will also divide 4. So there is no need to draw that edge between 1 to 4, because that will be taken care by the transitive property of the partially ordering. Now the next thing is 6. So I am writing a 6 here, and now since 3 divides 6, so I am drawing a line moving from 3 to 6. And then since 2 also divides 6, so I am drawing this line as well. So 2 divides 6. Now finally, we have 8 also. So I am writing 8 here. And since 4 divides 8, so I am drawing the line from 4 to 8. And we have 12 here. So I am writing 12 over here. And since 6 also divides 12 and 4 also divides 12. So this is the Hess diagram corresponding to this partially ordered set. And I repeat the important points that you need to keep in mind. First is that since it is reflexive, every loops we have removed from it. So the loops are redundant in this case. Since it is since it is anti-symmetric, so it is not going to move in the reverse direction. So we are always going to move in the upward direction. That if 3 is related to 6, because 3 divides 6, so I will be placing 6 over 3. Now you can see that 6 does not divide 8, so there is no path to move from 6 to 8, because we are always allowed to move in the vertical direction. So I can move from 6 to 8, but I can't move from I can move from 6 to 12, but I can't move from 6 to 8. Similarly, I can't move from 3 to 8. Right? Don't think that, sir, I can move from 3 to 6, 6 to 12, and then 12 to 4. No, the downward movement is not permitted. Only upward movement is permitted. So 3 to 6, 6 to 12 we can move. We can move from 1 to any of the element, because 1 divides every element. 1 divide 2, 1 divide 3, 1 divide 6. So I can move from 1 to 2, 2 to 6, or I can move from 1 to 3 or 3 to 6. 1 divide 4, so I can move from 1 to 4. 1 divide 12, so I can move from 1. But if a particular element, like you can see that here 6 is not dividing 8, so you can't move because there is no edge between 6 and 8, and you are not allowed to move in the downward direction. So that is why you can't move from 6 to 8. So this is a diagrammatic representation of the partially ordered set, and this diagram is known as the hash diagram, right? So I hope you have understood that how to draw it. We are going to take some more example to make more sense of hash diagram, right? So let me take this example here. This is also a very beautiful example. Now suppose I have to draw the hash diagram on the power set of hash, and this example I have taken earlier also, so I will be drawing it quickly. So what is the power set of S? The power set of S contains empty A, B, A comma B, sorry, A, B, C, then A comma B, then B comma C, then C comma A, then A comma B comma C. Yes, ladies and gentlemen, I hope you are getting. Now to to write the hash diagram, first I am taking the empty set here in the bottom, and empty set is a subset of set A. So I am drawing the set A here. It is a subset of set, let me write the set C here, and let me write the set B here, right? Now it is subset of each of the set, so I can draw the line moving from all of them. Now let me write here A comma C. Let me write here B comma C, and let me write here A comma B, and let me write here A comma B comma C. Okay. So now draw the lines in the vertical direction. So A is a subset of AC. This set is also a subset of AC. B is a subset of BC. C is a subset of BC. A is a subset of AB. B is a subset of AB. And if I take ABC, AB is a subset of ABC. AC is a subset of ABC. And BC is a subset of ABC. Now this is the hash diagram representation of the partially ordered set that is defined over the power set of S, right? So you can see that it looks very nice and very clean, and it gives us clear idea that how the elements are related to each other. We can see that C is related to BC, C is related to AC, C is related to ABC, but C is not related to AB, right? Because you can't move from C to AB. Yes or no? And just by the previous example and this example, we also want to understand the comparable and non-comparable element. So if I ask you that whether 8 and 12 are comparable, then 8 and 12 are not comparable, because, or incomparable, because neither 8 divides 12 or 12 divides what? Similarly, 4 and 6 elements are non-comparable element. Here 2 and 3 are non-comparable elements, right? 2 does not divide 3 and 3 does not divide 2. So they are non-comparable means what? That there is no path from one element to the other element, or other way around also, means there is no path from 3 to 2 and 2 to 3. There is no path between 4 to 6 and 6 to 4. Here also, if you look at these elements, suppose I say A, B and C, then these are non-comparable or incomparable element, because there is no path from B to C. Don't think that, sir, I will go like this and then come back. You are not going to move in the backward direction. So A, B, C are non-comparable. Similarly, AC, AB and BC are non-comparable, right? Phi is related to every element, so that is why you can move to each of the element from phi. So you can move from phi to B, phi to C, phi to A, phi to ABC, phi to AB, and all other elements as well. Okay. So I hope you are understanding that how the hash diagram is drawn. I am going to draw the hash diagram of this partially ordered set as well very quickly. So we have the element 2 here, right? And 2 divides 4, so I am writing 4 over 2 and I am drawing a line. Then we have the element 5. Now sometimes students get confused and they think that 5 is more than 4, so it should come somewhere over the 4. No, I will write 5 over here, and I hope you will agree to it. Why I will write? Because 2 and 5 are non-comparable element, and 5 does not divide 4 and 4 also does not divide 5. So suppose I take 10, so I write 10 over here, and then 5 divides 10, then there is a path from 5 to 10, and since 2 also divides 10, so there is a path from 2 to 10, right? We have 12, so I am writing 12 over here, and since 4 divides 12, so there is a path from 4 to 12, and then we have 20, so I am writing 20 over here, and since 10 divides 20, so I am writing 10 divides 20, and 4 also divides 20, so I am drawing this path also. Now we have 25, so I can write 25 over here, and since 5 divides 25, I can join this path. Now don't get confused that why we are writing 25 below 20, because it is not the size or the what you call weightage. What is the term that I should use, like the value of the number? Actually it is the relation, the divisibility characteristic of it, because the relation is defined on the basis of divisibility characteristic of it. So that is why it is being written in this order. Next that we are going to discuss, next thing are very important, and it will help you to get better idea related to the partially ordered set as well. So there are some important terms. First let us look at their definition, each of them one by one. So what is the maximal element? An element of a partially ordered set is called maximal element if it is not less than any element of the POSET. The element A is maximal in the POSET if there is no B in S such that A is less than or equal to B. I hope you didn't get the definition, right? You will get it, just wait. I will take the examples to explain this. But before that, let us look at the definition of minimal element as well. An element of a POSET is called a minimal element if it is not greater than any element of the POSET. That is, A is minimal if there is no element B in S such that B is less than A. So to understand this, I am going to look at the previous examples, right? The examples that we already have discussed. Now suppose in this partially ordered set, if I ask you that what are the maximal element, so what will be your answer? The maximal elements are element 8 and element 12. Why 8 and 12 are maximal element? Because 8 is not less than any other element in the partially ordered set. Yes, S is not less than any other element in the partially ordered set, and similarly 12 is also the maximal element because 12 is also not less than any other element in the partially ordered set. See the definition of it. What is the definition? It is called maximal if it is not less than any element of the POSET, right? So here 8 and 12 are the maximal element. 4 is not maximal. Why 4 is not maximal? Because 4 is less than 12, 4 is less than 8. 6 is not maximal. Why? Because 6 is less than 8, 6 is not less than 8, 6 is less than 12. 2 is not maximal. You can see it is less than lot of element. So the maximal elements are here 8 and 12. What are the minimal element? The minimal element is 1. Because 1 is less than every other element, and if you look at the definition, it says you that a POSET, the element of the POSET is called minimal if it is not greater than any element of the POSET. So 1 is not greater than any element of the POSET, right? So 1 is the minimal element. If I take this example, in this example 5 is the minimal element and ABC is the maximal element, right? If I take this example, this is important to understand. The maximal element are 12 and 20. Is there any other? I am taking a pause. You answer. Yes, 25 is also the maximal element because 25 is not less than any other element. So there are 3 maximal elements. Don't look at where they are coming. I could have drawn 25 over here also, like I could have drawn a line, because it should not be confused that 25 is coming below this element, so it is not maximal. We are looking at the characteristic of it. So the maximal element are 12, 20 and 25. And what are the minimal element? 2 and 5. Okay. So I hope the maximal and minimal elements are making sense to you. The next thing that we are going to talk about are greatest element and least element, and after defining the terms, I am going to take separate questions. Lot of questions will be solved in the either this video or in the next video, where I'll be separately discussing about all these terms on a particular particular partially ordered set. So let us understand the definition of greatest element. An element in the POSET that is greater than every other element is called the greatest element. That is, A is the greatest element of the POSET if B is less than or equal to A for all B in S. The greatest element, if exists, and that is important, the greatest element is unique when it exists. So it is also possible that the greatest element may not necessarily be there. Right, I will take examples, don't worry. And then what is the least element? An element is called the least element if it is less than all element of the POSET. That is, an element A is the least element of the POSET if A is less than or equal to B for all B in S. Right, and the least element if is unique, this is unique when it exists. So uniqueness thing you need to keep in mind. Now to understand this, suppose I take simple example like this, and so that you get the idea that what are the, so suppose I say that these are the picture related to different partially ordered sets, right? And if I look at the first one, what are the maximal elements? So the maximal element are B, C and D. And what is the minimal element? Minimal element is A. If I ask you that whether we have a greatest element in this, what is the definition of greatest element? Greatest element is it should be greater than every other element of the partially ordered set. But if I say that, if I look at this example, none of the element, if I say that B is greater than C, no. Whether B is greater than D, no. They are maximal element because they are not less than any other element, but certainly they are not greatest because B is not greater than C or D. Similarly, C is not greater than B or D. So B, C and D are maximal element, but none of them is the greatest. And what is the minimal element? A, and A is also the least element because there is no other element which is less than A. So that what is the definition of least element? You see here that least element that of A is that it should be less than or equal to B for all elements. So here A is, this element A is less than every other element. It is less than this and this and all other element, right? If you look at this example, what are the maximal element? Maximal element are D and E. Is there any greatest element? No, there is no greatest element. What are the minimal element? A and B. Is there a least element? No, there is no least element. If you look at this example, what is the maximal element? D. What is the greatest element? Also D. What is the minimal element? A and B. What is the least element? No least element. If I ask you what is the maximal element? D. What is the minimal element? A. What is the greatest element? D. What is the least element? A. So whenever the greatest and least elements are existing, then they are unique. Now look at the previous examples that we have talked about. You agreed that here 8 and 12 both were the maximal element, but if I ask you what is the greatest element, so here there is no greatest element. 1 was the minimal element, but what is the least element? Yes, 1 is the least element as well. If you look at this example, in this ABC was the maximal element and phi was the minimal element. So ABC is the greatest element also because all other elements are less than ABC, and phi is the least element because all other elements are greater than phi. If I come here and if I ask you, is there any greatest element? The answer is no, there is no greatest element. We had 12, 20 and 25, as the maximal element and 2 and 5 as the minimal element, but none of them out of 12, 20 and 25 are the greatest, or none of them out of 2 and 5 are the least element, right? So I believe that you all have understood that what is the minimal element, what is the maximal element, what is the greatest element, what is the least element. So what is an upper bound? For defining an upper bound, first of all we talk about a subset of the POSET, and if we have an element U in S which is greater than or equal to every element A in the subset A, then we say that U is an upper bound of A. Similarly, an element L of S is said to be a lower bound if L is less than or equal to A for all element in the subset, right? I will explain through examples, because examples are the best way to understand the thing, but definition you should be clear about in the beginning itself. What is least upper bound and what is greatest lower bound? So as the name itself suggests that least upper bound is least among all upper bounds and greatest lower bound is the greatest among all the lower bounds. So that is what the definition is suggesting. Mathematically it is written like this. You can pause the video and note down the definition. So I am directly jumping to the problems through which you will be able to understand. So as you can see that in the figure I have a POSET, right, and I am going to take a subset of this POSET, that is ABC, and for ABC I am going to find all upper bounds of ABC. So first of all let us identify the element A, B and C. So these are the elements A, B and C. Now if I talk about the element E, we note that the element E is greater than element B, it is greater than element C and it is greater than element A. So E is an upper bound. Now let us talk about D. So D is greater than B and D is greater than A, but D is not greater than C. I hope you have seen the idea of comparable or incomparable element, because here D is not comparable with C. So D is not greater than C. So D can't be an upper bound. Now since E is an upper bound and F is greater than E, so because of transitivity F will also be an upper bound. Not much confusion here. And because F is an upper bound, then H and J will also be an upper bounds, right? It will also be the upper bounds for this set ABC. So did you notice this or not, that when we are talking about upper bound of a subset of the POSET, we are looking at all those elements which are greater than each of the element of the subset. Means we are also we are looking at the elements which are greater than or equal to A, also greater than or equal to B and greater than or equal to C. It should be greater than or equal to each of the element in the subset, right? So these are the upper bounds. Okay, these are the upper bounds. What are the lower bounds of ABC? Now if you look at the element ABC, I hope you will all agree that A is less than or equal to A, because it is a POSET, so it is reflexive, and A is clearly from the image that it is clear that A is less than or equal to B and A is less than or equal to C. So A is less than or equal to all the three elements in the subset, so the lower bound will be A. So we have one lower bound, that is A, right? Now let us take another example. So let us take the next example where I am going to talk about the J and H, the subset J and H. So for J, this is the element J and this is the element H, and we can clearly see that there is no element in the POSET which is greater than or equal to both J as well as H, right? J and H are non-comparable element and there is no element which is greater than J also and H also. So for this there is no upper bound, right? So upper bound may be there, may not be there for a particular subset. So here there is no upper bound. But if I ask you that what are the lower bounds for J and H, then clearly F will be a lower bound because F is less than J and H both. Clearly D will also be a lower bound because you can see that D is less than F, and because F is less than H and J. So let us write it lower bound so that we don't miss the things. So what will be the lower bounds? There will be a lot of lower bounds in this case. F will be a lower bound, D will be a lower bound, E will be a lower bound, B will be also a lower bound, C will also be a lower bound, and A will also be a lower bound, right? So A, B, C, and D and E and F all are lower bounds. But G is not a lower bound because you can see that G is less than H, but G is not less than J. So G is not a lower bound except G. All other elements like A, B, D, C and E, F are lower bounds. How many of them are there? 1, 2, 3, 4, 5, 6. Here we have noted down the 6. Now let us take the other subset here, that is A, C, D and F. And let me remove this sign here so that we can clearly see. So we have A, we have C, we have D and we have F. So what will be upper bounds in this case? And I hope you have understood the definition, that we are going to look for all those elements which are greater than and equal to all the elements like A, C, D and F, right? So this is important because the students in this example will make mistake. So did you notice that F is greater than or equal to F, right? Because every element is associated with itself. F is also greater than or equal to D. F is greater than or equal to C as well, and F is greater than or equal to A as well, right? So F will also be an upper bound. The students don't consider that element, they just ignore that, so don't make that mistake. So F is one of the upper bound, and since F is an upper bound, then because of the transitive property, J and H will also be an upper bound, right, gentlemen and ladies, of course. And what are the lower bound in this case? So let us talk about the lower bounds. So clearly you can see that A is less than or equal to A is less than or equal to C, A is less than or equal to D, and A is less than or equal to F. So A is a lower bound. Is there any other lower bound? What about B? So if I take B, B is not less than or equal to C, so B can't be the lower bound, right? And if I take E, E is not less than or equal to D, so B can't be the lower bound, E can't be the lower bound, D can't be the lower bound because D is not less than or equal to C. So only lower bound here is equal to A. Pause the video and watch it carefully because there may be some confusion. So don't rush to it, just pause it and check whether you are getting it or not. So there are 3 upper bounds, that is F, J and H, and there is just one lower bound, that is A. Now let us solve the last problem which is given here. So they are asking us to find that what is the least upper bound and greatest lower bound for the subset, that is A, B and G. So if I talk about B, D and G, what are the upper bounds? So let me write, we have a subset B, D and G. So first let me write the upper bounds. So what is B here? B, this is B. Where is D? This is D. And where is G? This is G, right? They are in one line. So upper bounds are clearly H and H, not J, because J is not greater than. So H is an upper bound, and you know where the students will make mistake? They will not consider G as an upper bound, but be mindful of that. G will also be an upper bound because G is greater than or equal to G is greater than or equal to D, and G is greater than or equal to B. So of course H is an upper bound, but G is also an upper bound for this subset. And we have two upper bound, G and H, right? So out of these, which one is the least? So the least upper bound is G, because G is less than or equal to H and G is also less than or equal to G. So the least upper bound, that is what they were asking in this question, for B, D and G is equal to G. And what are the lower bounds? So here again students will make mistake. They will consider that the lower bound is A only, but don't make that mistake. A is of course a lower bound, but since you notice that B is less than or equal to B, B is less than or equal to D, and B is less than or equal to G, so B is also a lower bound. So out of these two lower bound, A and B, which is the greatest? So greatest lower bound is equal to B. So I hope by this example you have understood that what is the least upper bound and what is the greatest lower bound. Okay. Next we are going to talk about a concept which is known as lattice. And to understand lattice, you should be very much clear about the concept of least upper bound and greatest lower bound. So a partially ordered set in which every pair of element, and mind it, every pair of element has both a least upper bound and a greatest lower bound is called a lattice. And here we have some examples to understand that which of them is a lattice. These are all the partially ordered set. So you can clearly see that this example we have, if you take any two element, for example you take the element B and D, right? So B and D will have, what will be the lower bounds of B and D? A and B will be the lower bounds of the set B and D, means this pair of element. And what will be the greatest lower bound? Greatest lower bound will be B. And what will be upper bounds of B and D? Upper bounds of B and D will be D, E and F. And what will be the least upper bound? So least upper bound will be D. Similarly, you can verify, and this is something which is time consuming process. So you can verify. You take for example the element F and E. So what are the lower bounds of elements F and E? Lower bounds are E, C, D, B and A. So what is the greatest lower bound? Greatest lower bound is E. What are the upper bounds of E and F? Upper bounds of E and F are E and F both. Don't miss to consider E as the upper bound. Now what is the least upper bound? Least upper bound is E. So for this you can clearly verify that if you take any element, any pair of elements, sorry, you will always get a least upper bound and a greatest lower bound. So I am leaving this for you as an exercise to verify that whether you are able to find out the least upper bound and greatest lower bound for every pair of element or not. And put your answer in the comment box in case if you are not able to verify. If I take this example, in this example I have one pair of element which I can clearly see. For example, if I take the pair of element B and C, then what are the upper bounds of B and C? So the upper bounds of B and C, you can see that E is an upper bound because it is greater than B and C both. D is an upper bound because it is greater than B and C both, and F is an upper bound. So we have three upper bounds, that is D, E and F. But if I ask you, can you decide which one is the least upper bound? So because D and E are non-comparable element, out of D, E and F you won't be able to find out that which one is the greatest least upper bound, right? I rephrase my statement. We have got upper bounds like D, E and F, and out of that you won't be able to find out that which one is the least upper bound. So out of upper bounds we have to find the least one. So because for this element, this pair of element, a pair of element like BC, we don't have a least upper bound, so this is not a lattice, not a lattice. The first example was a lattice. Similarly, you can verify that this will also be a lattice, and I leave this for you to verify. So with this, I believe that I will end this video. Right, in this I have discussed about a lot of things. I'll be creating one more video where I'll be solving more problems. So thank you, subscribe the channel, and happy watching.